In this session, I will be discussing heat question from 2014 support seminar paper. Capital A, then under that one, simple A, state Newton's law of cooling. Okay, what is the Newton's law of cooling? Okay, so the rate of loss of heat of a body is directly proportional to the temperature difference between the surrounding and body, between the body and surrounding. Okay, I repeated it. The rate of loss of heat of a body is directly proportional to the temperature difference between the body and the surrounding. Okay. Okay, then they ask valid conditions. What are the valid conditions? Temperature difference between body and surrounding is small. It should be small. Then surrounding temperature should be constant. That means remain unchanged. What else? And also for this one, very especially, uh, cooling mainly should be occurs by convection. Okay, these things you should write at least two of them because this is a plural one. That means state the conditions. So you have to give just 1 point is not enough to get full marks. Okay, then a student design an experiment to demonstrate the physical properties of wax using the above law. Solid wax was heated uniformly and its temperature was measured with time until the state just before it begin to vaporize. Okay. Draw the expected graph of its temperature with time. Okay. Okay. They ask you to first draw the graph. So it should be just before the vaporization. So then, so this is for the actually part B. Okay, part B. So the graph should be like this way. Okay, this is time in seconds or minute or whatever. They are mentioning the rest in minutes, so I am putting here the minutes. Okay, here the temperature, let it T in Celsius. It should be increased. Initially, it should be at room temperature, and now it should be increased like this way. Okay, this is solid. Initially, it was solid, so initially, yeah, it was solid. So now, what they are asking? Okay, It should be like this, isn't it? So then the student obtained these readings by heating 100 gram of wax in calorimeter of heat capacity 60 joules per kilogram. Okay, it should be changed like 60 joules per Celsius, ne? Using a heating element of 100 watt. The details obtained by the graph are as follows. Temperature of the environment is 30 Celsius. So that means this one should be 30, ne? Isn't it? It should be started 30. Okay. Then the gradient of the tangent drawn to the graph just before the wax begins melt is 3.6 yeah 3.6 Celsius per minute. Okay, that means it should be like at this point, so I'm using a different color. So I'm gonna use this one. So that means it should be at this point, the gradient. So they said that gradient at this point is 3.6, isn't it? 3.6. They say it is Celsius per minute, ne? Okay, so gradient at this point. Okay, then what they said? The constant temperature obtained by wax is 62. So that means it should be definitely at this point, isn't it? So this one is 62. So this one is 62 Celsius. Okay, that should be the melting point. Okay. The time that the temperature of the wax remain constant is 20 minutes. So that means from here to here to there, this is 20 minutes. Then this is 20 minutes. So I put it here because I already put the values there. Then this should be 20 minutes. Okay. Then what they ask, what they give. The gradient of the tangent drawn to the graph just after the wax completely melts. Okay, here they mistakenly mentioned that one. They completely melt. That means this one, this region, this region it. Okay, completely melt is 4.8 Celsius per minute. Okay, so here that means definitely it will again start increasing the temperature. Here we have another gradient, so that is a bit higher gradient. So that is another gradient is given here. So what it is, the value for that gradient, it is 4.8 Celsius per minute. So 4.8 Celsius per minute. Okay, I got some values here. Now what? Specific heat capacity of solid wax used above is 1800 joules per. Okay, here it is 1800 joules per kilogram per Kelvin. Okay, find the melting point. It is exactly 62. Ne? This one is that exact value. Ne? This one, isn't it? So this one is that exact value. This one, that means the answer should be 62 Celsius. Ne? Melting point. Yeah, it is 62 Celsius. Okay, it is 62 Celsius. Then find the rate of absorption of the heat by the calorimeter and wax just before wax begin to melt. Okay, just before the wax begin to melt mean this point, eh? Isn't it? It should be this point. In this region, it is the just before the melting, eh? So they are talking about this one. So we have to consider that point. Okay, I'm going to consider that point and I'm going to write some equations for this region. Okay, so let's write something related to that one. Okay, now what? Okay, now what we can do? Wait. Okay. They ask find the rate of absorption of heat. Okay, rate of absorption of heat. So there are two things. One is here we have two things. One is calorimeter, other one is that wax. Okay, I here draw the only calorimeter and the wax also they are inside this one. Inside this one that wax also. Let's draw it in this color. Okay, here inside this one we have what the solid wax. So the both of them, the calorimeter and the wax, here the both of them. This is wax. Okay, so this is where they heat up using a heater. This is wax, and this is a this is the calorimeter. Okay. Okay. Now look at here very carefully. Cal calorimeter. Okay, calorimeter is here. Then the both of them absorb the heat, so I have to write the equation for the both of them. So what are those? Okay then. Okay. Now let's write the equation for this one. The heat absorption. Okay, so we can say the heat is equal or absorbed heat is equal Q is equal what? For the wax it is MC delta theta, MC delta theta, plus for the calorimeter it is yeah, it is just C dash delta theta. Okay, why? Because they already given the heat capacity of the calorimeter. So this C dash is heat capacity. So heat capacity into the temperature change in temperature is already given the what the amount of joule it absorbs. So here the Q is equal mc delta theta. That is actually the very fundamental equation, mass into specific heat capacity into change in temperature. So what you have to do here, we don't know the actually the change in temperature, but we know the rate of change in temperature. So what I have to do, I have to divide the whole equation by T. Okay, I divide the left side by T and the right side also by T. Okay, now what we can do, um, delta, here we have the delta theta over T, here also we have the delta theta over T. So I take it out. Okay, so here we have left hand side we have what Q over T. Okay, that is equal. So here we have MC plus C dash, and I am taking that delta theta over T out. So this one I take it out. So instead of this one, what we can write? This is a delta theta. Delta theta over t is equal actually what? So it is equal here the value 3.6 Celsius per minute. So but I have to convert that one into the Celsius per second because the rest is given by the SI unit. So for this equation, so I have to convert that one into the what? Yeah, into the Celsius per second. So what I am going to do, I'm going to write some equation related to this one. So it is the delta theta over t here, delta theta over t, that one is actually 3.6 Celsius per minute. Per minute mean, yeah, per minute mean it is in the denominator, isn't it? So per minute mean just minute in the denominator. Okay. Now the minute mean I can put the 1 minute, just 1 minute here. Now what I have to do, I can divide I can instead of 1 minute I can put the yes 60 second, isn't it? Or in the other way also you can write this one, nah? Okay, I'm just substituting the values. 3.6 divided by 60. This is second. This is Celsius. So so what it is? So what is the answer for this one? You can write the answer. So dividing by 6 is just 0.6. Or I can take the two decimal points leftward, then 0.6 yeah, it is 0.6 into 100. Then here we have the 0.6 times 1, 0.6 times. Yeah, what it is? Actually 6. So 6 into 10 to the power minus 2 is the answer. 6 into 10 to the power minus 2 is the answer. Okay. So instead of this one, I can write the 0 point, yeah, 0 0.06 or uh, yeah, 0.06. Yeah, 0.06 I can write it here. Now what? It should be Celsius per second. It should be Celsius per second. Okay. If you have any doubt, just tell me. Yeah. Okay. Now it is. We have that tilde theta over t with the SI units. So now what we can do? I have to just substitute the values. Okay. Okay. Now what are the values for this one? The mass of the wax, it is 100 gram. Yeah, 100 gram means 0.1. 0.1. Okay. 0.1 into C is 1800. Okay. 1800 plus C dash is specific heat. Sorry, just heat capacity. It is 60. Okay. Then not instead of this one, I can write 0.06. That the value I delta it over T. Value I got it from that one. It is 0.06, so I just have to multiply it by this one. So here we have what 180 multiplied by 0.1 is 180 plus 60 is 240. 240 into 0.06 is just what? Hmm, 0.06 into 240. That means 6 into 20, 2.4. You can just multiply that one. 14.4. So the answer is 14.4. So the answer is 14.4. Can you hear me very clearly? Uh, hope you all can hear me very clearly. Okay. Now here we have what? Here we have QOT. Here we can simplify this one. Then the answer is 14.4. It is actually joules per second, or we can say watt. This is actually QOT. Now what they ask you to find? This is the one they ask you to find in part 2. Ne? Find the rate of loss of heat to the environment at the moment. Okay. Now they ask you to find the rate. So rate of heat loss. Ne? Rate of heat loss. So rate of heat loss. Rate of heat loss. So it should be equal what? So the rate of heat supply minus rate of heat supply, rate of heat supply minus what? Rate of heat absorbed. Abs- So rate of heat supply is actually is 100 watt. Ne? 100 watt. So that one minus this one. Ne? This is the rate of heat absorbed. No. Sorry, 14.4. I can write it like watt. So this is what? 85.6. Ne? Okay, isn't it? It should be 85.6. 85.6. So this is the rate of heat loss to the surrounding in this case. Okay, then the next question. Calculate the specific heat capacity of liquid wax and the specific latent heat of fusion of wax. Okay. First of all, we have to calculate the heat capacity of liquid wax. So for this one, we can do this kind of thing. Ne? Okay, now look at here. Let's come to that graph. Okay, here we have the graph. Let's come to that one. Okay. Now, whatever here you can see this one. This is the liquid, ne? This is the liquid form. This is the solid, ne? This region is solid. This region is for the what? Liquid form. So what we can do, we can say the rate of heat absorption during this period. That means just before the melting should be equal to the rate of heat absorbed by the liquid also. Okay, so not just the cooling rate of cooling, that means, but the rate of heat absorbed by the this one, that the same wax in solid should be equal to the rate of heat absorbed by the what wax in the form of liquid. So, so not just, but it is not just only wax, but the calorimeter also. Yeah, okay, let's go to that one. But now we have the this rate of cooling 4.8 Celsius per minute. No, it should be Celsius per minute. Yes, Celsius per minute. Okay, now let's go to the other this part. But we already found that this is what the rate of heat absorption is 14.4. We already have this one. We got that value. So what I am going to do, uh, I'm gonna equate what rate of heat absorbed by the calorimeter plus what wax. Okay, now look at here very carefully. Rate of heat absorbed by wax plus calorimeter. Yeah, this one we already calculated. This is 14.4. Should be equal what? Okay, so here the wax is actually solid, ne? Solid form. So here, what? Again, same thing. Okay, now look at here very carefully. So this is also rate of here the rate of heat absorb. Okay, rate of heat absorb. Ne? Okay, now look at here very carefully. Heat absorbed by wax. Again wax. Okay, wax plus calorie. So now the wax is in liquid form. Okay, okay, okay. This is in liquid form. Now what we have to do? So we already got the value for this one. Eh? This one we already got the value. Is 14.4. So this should be equal rate of heat absorbed by the wax. So that one we can write like, so m, let it C naught delta theta. Yeah, so delta theta, yeah, over t. So the both side, actually this one, this side, left side we have already did. Now just wait. So plus rate of heat absorbed by the calorimeter. But then now this theta is actually, this time theta is bit different than previous theta. Delta theta. Now what we have to do, I have to divide by the time. Otherwise, so it is not possible because the left hand side we have what? Left hand side we have the rate of heat absorbed. So the right side also should be the same thing. So I have to divide by the t. Now what we can do? Actually, we can take that delta theta over t. So we have m. Look at here very carefully. M C naught. C naught is the specific heat capacity of uh, what wax in liquid form. So MC naught plus C dash, okay, times what? Yeah, delta theta over T. Okay. So this is equal to actual what? 14.4. Okay, now what we have to do? We have to just substitute the values and find the C naught. Okay, so this one is actually what? This one mean is delta theta over the rate of change in temperature. So it is equal what? This one is 4.8 Celsius per minute. So the same thing here but it is also per minute. So I have to again convert that one also. So it is 4.8 Celsius. Yeah, I have converted that one. So it is delta theta over. I use different color. So it is delta theta over what? T. So it is what? 4.8. 4.8 Celsius per minute mean 1 minute. So it is now look at here very carefully. 4.8 Celsius over the 60 seconds. So dividing by 60. Dividing by 60 is 0.8. And 60 mean 0.08. Okay. 0.08 Celsius per second. Okay. 0.08 Celsius per second. Okay. So this is it. This is the delta theta over T for this one. They say for the when it is just after the melting. So now what I have to do? I just have to substitute that value to there. Okay. Okay. Just substitute the values here at 0.08 for this one. For this one, okay. Now I can write complete this one. M is actually the mass of the wax. We can say it is remain unchanged. C naught is the one who we want to find. C dash, what is C dash? C dash is the heat capacity of the element. It is 60, isn't it? It is 60, right? Yeah, I think it is 60. Yeah, it is 60. This is 60 and whole thing into what? 0.08. So you have to multiply this side by this side and both side by what 100. Then we have the 8. Here we have 1000. Yeah, 440. So 1000, isn't it? I multiplied the whole equation by 2. Okay. Now what I have to do? Look at it very carefully. Yeah. Okay. Now I have here 1440. Then here we have what? 0.1 into 0. This is 60. And also into the 0.08. Ne? Just that 0.08. This one. Just take it other side. Okay. That's a division. Ne? So I took that one here. Then 0.8. So this one divided by, oh no, yeah, it is not 0.8. Yeah, I multiplied the both side by 100, then this is just 8. Ne? So dividing by 8 is, but it is 180, right? Isn't it? Yeah, it is 180. The answer was this one, 180. Now look at here. Look at this one very carefully. This is 180. That is equal what? 0.1 into C naught plus this one is what? 16. Take that 60 other side. So 120. Then 120 is equal 0.1 times C naught. So that means 1200 ne? Joules per kilogram per Kelvin. This is what we have. C naught. C naught is the specific heat capacity of the wax in the when its form is liquid. Okay. Then what they ask you to calculate? Okay, latent heat of fusion of wax. Okay. Then again we have to go back to that graph. Latent heat of fusion. Okay. Here that solid. And here we have the solid. Here we have the liquid. So actually that solid is changing to the liquid form, isn't it? So this is the fusion. Okay. Fusion period. So we can say that the temperature does not change during the fusion period. So the temperature of the wax and the temperature of the calorimeter does not change during this period. So we can say that the total amount of, yeah, the total amount of, since the temperature does not change, so from here to there, we can say the total rate of heat absorbed by the system is totally goes to the that fusion. Okay, so the fusion of the wax, isn't it? Because the temperature does not change, so the total heat and total rate of heat absorption, okay, should be goes to the fusion, rate of heat absorption. So due to the fusion, so we can equate that too, isn't it? Because the temperature does not change, so the calorimeter does not absorb the heat. So some amount of heat definitely goes to the surrounding, but we are considering this value, because that value should be the here. Okay, this value I am considering this value. So this was the value that absorb, isn't it? The rate of heat, yeah, that is the rate of heat absorbed by the system. So the rate of heat, so during this time period, that means within that 20-minute period, so there is no temperature change. That means the rate of heat absorbed by the calorimeter is 0. So the rate of heat absorbed totally, that total heat should be goes to the that fusion process. Okay. So we can calculate using that one. We can calculate the what specific latent heat of fusion. Okay. So within that 20 minute period. Okay. Within that 20-minute period. within that 20-minute period. So we can say that 14.4 joules per second totally goes to the fusion process. Okay, so then what we can say, we can do that calculation. So now I'm gonna do that one. Okay, now what we can say, that rate of heat absorption, rate of yeah, heat absorption. Yeah, that should be equal. But so that this is for the previous rate of heat absorption should be equal rate of heat absorption for the fusion, and during fusion. So rate of absorption. So actually, so this is actually during the process of fusion. Okay. So this is the previous one. This is for the previous one. This is for the that fusion. Okay. Okay. This is for the fusion. This is for actually the previous case. Previous meaning that is when it is yeah, the change in temperature. So this is for that previous state. This is previous process, isn't it? So then we already know that this is 14.4, ne? That is 14.4. So we can calculate. We don't need to calculate it again. Just we can put that 14.4 joules per second. So that should be equal to the rate of heat absorption during the fusion process. So the mass of the wax is, let it m. So m into L is the heat absorbed by the wax during the process of fusion. So we have to divide that one by the T. Okay, now what we have, actually we have that values, isn't it? We have the time and all the things. So this is 14.4. So this is 14.4. So that value, then m is 100 gram. So it is 0.1. L actually, that is the value we want to calculate. This is 20 minutes. So we have to convert it into the second, because these things we are putting with the SI units. So this is 20 into 60. Why it is what it mean, the 20 into 60? That is 20 minutes into 60. Yeah. Okay, so 20 minutes is there. So that one we have to convert into the seconds. Okay. So then take these things, these two into the other side. Then just we have you have to multiply it by that one. It is 1200. So that 14.4 you have to multiply it by 1200. So it is it 14.4? Yeah, it is 14.4. So you have to multiply it by 1200, because this is 12 two zeros, that means 1200. Then again you have to take this one as a division. So it is what? Then dividing by 0.1. Okay, so the answer is Answer for L is, okay, from this one you can calculate the L. How you get it? Take this one into the numerator. In the other side, take this one into the denominator of the other side. So it is 1 point actually 1.728 into 10 to the what? 10 to the 5. It is 10 to the 5. So this one actually joules per kilogram. Okay, this is joules per kilogram. Okay, and that is it. 1.728 into 10 to the 5. So I put the 1.72. Or we can say that it is just 1.73. So 73 into 10 to the 5. Okay. Then the very last one, what it is. Then when the heat is applied continuously to the liquid wax, he observed that after a certain situation, wax remain as a liquid. That means it does not vaporize. Ne? Okay, you can underline that one. Wax remain as liquid. Okay, if you can grab that point, then you should understand that it is not, yeah, it is not come to the that ne- uh, it does not reach that wave ne, boiling point. Okay, so it does not reach to the its boiling point. Ne? Why they mention these kind of things? See, wax remains as a liquid and its temperature does not increase. Okay, that means it does not come to the boiling point. I mean, initially they say it is still the vaporization. They supply the energy like that way. But now something is something different. Ne? Okay. Explain the reason for this and calculate this steady temperature. Okay, now I am going to back to that graph. Okay, where is it? Okay, this is the graph. Now what happened? It increase that temperature up to some level, then again it stayed at a constant temperature. So why again it came to the constant temperature now? Okay, here I have to erase this view of this. Now look at this one very carefully. So some again another different constant temperature. Ne? So look at here. This is it. This is that something different constant temperature. Let it theta. Okay. Let it theta. So they ask you to find the reason and calculate that temperature. So what we can say. So explain the reason for this. Why? The rate of heat absorbed by when the continuously they supply the heat to the this one. Continuously they supplied the heat to the this one. But still what happened? The rate of heat absorption by the system is equal to the there is some special situation, the rate of heat absorption by the heat system after it melt. Okay, the rate of heat absorption by the system is equal to the rate of heat loss to the surrounding. Okay, that means it come to some equilibrium. Okay, that means heat absorbed from the heater is rate of heat absorbed by the from the heater is equal to the rate of heat loss to the surrounding. So that is the reason. So it come to the equilibrium position, equilibrium state, then not the rate of heat absorption by the system is equal to the rate of heat loss to the surrounding. So due to that reason, there is no temperature increasing. So it won't come to the that's boiling point. Okay, so it has to stay some some temperature below the boiling point, because the rate of heat supply from the heat to the system is equal to the rate of heat loss to the surrounding. Okay, now what we can do, we have to calculate the temperature, but here the during this process, so the 85.6, so the cooling, the Newton, I'm gonna use the Newton's cooling law, and I assume that this is okay. This is the uh, heat loss. This is the heat loss during the that process, ne? That process mean yeah, in the very beginning, ne, in the very beginning, that 14.4 is, ne, initially we put the this one, ne, when it is solid, when it is solid, so the rate of heat lost, so rate of heat loss to the surrounding is this one, 85.6, ne. So that one I can write one equation for that one, for yeah, when it is just at 62 Celsius, ne? When it is just at 62 Celsius, I can write the equation for that one. I think I can consider it as 62, ne? When it is just before the melting. So the just before the melting mean this is the rate of heat loss to the surrounding, 85.6. So we already calculated rate of heat loss. So it is 85.6, and the temperature of the that system at that point is this one, ne? So this one, so that is actually 62. Okay, now what we have to do, we have to use the Newton's cooling, yeah, Newton's law of cooling, the Newton's law of cooling for this one. So now I'm gonna use that one. Okay, now look at this one very carefully. So do you remember that equation? So equation for that Newton's cooling law is, okay, I write it with a different color. Okay, now what it is, delta theta, so delta Q over delta T, rate of heat loss, okay, is equal Ka times theta minus theta naught. Okay, what is these things? Delta Q over delta T is rate of heat loss. K is it is a just constant, depend on the its surface and nature. So what is the A? A is actually the surface area, theta is the temperature of the body, and theta naught is the temperature of the surrounding. So I can consider that at 62 Celsius, the rate of heat lost, this one is equal to 85.6, isn't it, brother? So we can use that one. This is what, 85.6, isn't it? So K we don't know, A we don't know, but the temperature of the system, it is just before the melting, it is 62, right? not 62.5. It's just 62 minus the room temperature. They have already given that room temperature. I think it is 30. Ne? Room temperature is 30. So this is the room temperature. That is 30. So you just have to substitute the values from for this one, this equation, and actually this is for the when it is 85.6. I think that value is correct. Okay, we already got that value. I think it is correct. Okay, just let me, yeah, 85.6, that is true. Okay, then when it come to this one, this temperature, we don't know the temperature, but still we know the surrounding temperature is 30, ne? Okay, so again we have to substitute the values because when it come to the equilibrium, so the rate of heat absorption is equal rate of heat loss to the surrounding. That means the total rate of heat supply to the system is actually equal to the what uh, the rate of heat element, ne? That means the power of the element, heating element, that is actually I think 100, ne? It is 100. So it is 100, just 100 equal. You can have to equal it. So this is instead of the delta Q or delta T, I can put the 100. So now the total heat is lost to the surrounding is equal Ka times. So the temperature, the body temperature, we don't know, but still we know the surrounding temperature. It is 30. So let this is the first equation, and this is the second equation. Okay, this is the second equation. So what we have to do, we just have to divide these two. Ne? We just have to divide these two, then we can get the answer. What we that means theta, that temperature we want to find. So what I am going to do, second equation divided by first equation. So 100 over 85.6. That should be equal. Yeah, in the numerator we have theta minus 30. So in the denominator what we have, Ka get cancelled out. So here we have theta minus 30. Here we have what? 62 minus 30. So what it is? Actually 32, ne? We can simplify this one, ne? The one, ne? So this is what? This is 32. So instead of the 62 minus 30, I put the 32. Now what we can do? Here we have the decimal point. Okay, we can take this one into the other side. So it is multiplication. Now what? Now it was in the denominator, now it is in the numerator. So 100 into 32 divided by 85.6. Okay, 85.6. So that is equals, yeah, theta minus 30. Okay. Now what we can do, I can simplify that values. This is 3000. Yeah, it is 3200. Okay, 3200. That whole thing should be divided by, yeah, 85.6. So it is 37. So the answer for this one, this simplification, 37. Okay, this is 37, roughly 37.4. This is theta minus 30. Okay, then what we can do, minus 30, take it other side. So 30 plus, so it becomes plus 30 plus 37.4 is actually we can find the final answer. So theta is equal to 67.4 Celsius. Okay, take this on other side. It becomes 37.4 plus 30, that is 67.5. 7.67.4. Okay, that is the final answer for this one. get this question. Okay. I hope you all understand these things. If still there is any doubt, just send me a WhatsApp message. Then I will help you to get the answers and get some knowledge about these things. Okay. So here I stop.